Hey, hello everyone. Today I'm going to teach the great details introducing chapter 3 of the textbook. The title of the chapter 3 is Mobile Charge Carriers in Semiconductors. So as we have learned, there are two primary types of carriers. What are they? Electron and hole, right? So electron is a negatively charged carrier in silicon, and the hole is a positively charged carrier in silicon. So electron holes are created in pairs in pure silicon material. However, in doped semiconductor, depending on what kind of dopant atoms are doped into the silicon material, the number of electrons and the number of holes are governed by the total doping concentration. For example, if arsenide is doped into the pure silicon material, say 10 to the 19 per cubic centimeter, then the total free electrons is identical to the total number of dopant atoms, arsenide dopant atoms, because arsenide comes from the column 5 in periodic table, so that it is working as donors in semiconductors. So column 5 atom, it has a fifth has a total 5 outermost electrons, so that only 4 out of 5 has been used to build up the covalent bonds with the 4 neighboring silicon atoms. Then single left electron, the fifth electron will be freed out, will become free in the silicon lattice, silicon crystalline material, so that it is roaming around within a silicon material, so that one arsenide atom can emit out a one free electron into the pure silicon material. So we can simply say that the doping concentration can determine the total number of free electrons per cubic centimeters. Okay, so I guess hopefully you have a fully understand the doping concentration, the meaning of doping, and how the silicon atoms are affected by the dopant atoms, as well as uh, if you can draw the energy band diagram for doped and undoped the silicon material, then that's good. Okay, so from now on, we're gonna apply a certain amount of electric field to have a force onto the mobile charged carriers such as electrons and holes. So how are they moving? That is the main question for chapter 3. So how the electrons and holes are moving around in the doped silicon material? Well, there are three primary types of carrier actions. Okay, so this action, let's see here, three types: one, two, three. So we're gonna first tackle out the physical meaning of drift in the silicon materials, which is doped, definitely. Afterwards, we're gonna study the mechanism of diffusion in silicon material. And lastly but not least, the recombination generation RG can be explained and understood as the third method how electrons and holes are moving in the silicon material. So let's read out each sentence for each concept. So drift, what is drift? Charged particle motion is described as drift. Okay, so a certain type of particle is moved in silicon materials. We can say that it is drifted. So what is the driving force for making drift? The driving force is influence of an electric field. Okay, here electric field. So without any electric field, we never imagine the drift. Okay, so always associate the concept of drift with electric field. Okay, so electric field is a key to to cause the drift. Okay, however, there is a one more condition. a certain particle is drifted or not? The answer can be found here. Charged particle. Okay. Electron, hole, both of them are charged already. How charged? Electron is negatively charged. Holes are positively charged. So any neutral particle, such as neutron, cannot be drifted even though there is electric field available. Okay, so two conditions: electric field is necessary, and the carriers or particles should be charged. Then we can say that, or we can expect the particles can be drifted by the electric field because they are charged. Okay, so we're gonna study some more details how to explain and how to model the drift in semiconductors. Second one is diffusion. So diffusion is very simple. Particle motion because of concentration gradient or temperature gradient. So because of these two reasons, doping concentration, no, not doping, just concentration gradient. Suppose that there is a silicon material, a piece of silicon material, and say that this is x of 0, and in a negative region of x lower than 0, the number of electron is 2. That's not full, but in the regime of x positive, the number of electrons is simply 2. Then what would be happened in this sample? The total number of electrons on the left hand side is 4, and the total number of electrons on the right hand side is 2. So simply speaking, we can expect the electron concentration gradient, right? So more electrons, less electrons. So electrons would like to diffuse toward right hand side. Is it associated with the electric field? Did I place a certain amount of electric field in this silicon material? No, right? So without any help from electric field or voltage difference, the diffusion can be happen. The driving force for occurring diffusion mechanism can be from the doping concentration gradient or concentration gradient. Well, of course, how come the more electrons can be found here? I can say I have doped more on the left hand side compared against the right hand side. Then we can simply expect more electrons existing on the left hand side compared against the right hand side. Um, the other mechanism, bring about the diffusion is a temperature gradient. Suppose that here 300 Kelvin and here 100 Kelvin. Suppose that you place the ice near to the right hand side, then maybe the the electrons in this regime, positive regime, x of x higher than 0, would have even though it has a more numbers of electrons, and the movement, the degree of moving of each electron would be kind of frozen out. So we may expect that the electrons at high temperature regime would prefer to move into the you know the low temperature regime. Okay, so this temperature gradient would also cause the diffusion. Okay, but it is nothing to do with electric field and any voltage difference for a given silicon sample. Okay, so diffusion is nothing to do with electric field. However, drift is very something to do with the electric field. Okay, so hopefully you may have some basic concept and intuition, uh, the main major difference between drift and diffusion. Okay, and third one is a recombination generation. this is very simple, concept. As we have learned, this crystal silicon material has been formed with the help of many covalent bonds, and these covalent bonds consists of two shared electrons coming from each neighboring silicon atoms. So once this electron is freed up, becomes loose, the bonding force becomes loose, electrons become free, and uh, it will also create hole left behind. So these electron holes are created in pairs in pure silicon material, definitely. Of course, in of the semiconductor material, this type of electron hole pairs are created in pair together. Okay, so these electron holes are created, which means electron hole pairs are generated. Okay, and this generation process is, canceled out by the other process, which is named as recombination. So I said a hole has been created here, and new free electron is created here. But at the other point, a hole is created and free electron has been generated, and this electron is roaming around in a pure silicon, no, no, crystalline silicon material, and it found that there is hole. Hole is usually has a lower energy state. Think of the energy band diagram again. A hole is created here and new free electrons are created. Say that electron is number one and this hole is number two. Okay, so in terms of energy of electron, from the perspective of this electron number one, this empty state is, has a very low energy state. So it would like to go into the lower energy state and it's going to lose its energy as the thermal energy. So electron holes now one and two, this guy and that guy is now recombined. Okay? So what happened right before recombination is happened? The electron is moved from right to left. What is the main result of this movement? Electron has been moved from right to left. Then we can say that current has been formed from left to right. Because of what? Because of this electron. Why this electron has been moved? Because it would like to recombine with hole. So we can say that this current is formed and generated by recombination, or simply speaking, recombination current has been generated. So charged particles such as electron hole, those two things are the main resource of forming current flow in semiconductors. And how they are moved in semiconductors, three different types of carrier reactions such as drift, diffusion, and recombination generation. How come recombination generations are, worded in together, worded in together? Um, because they are happened uh, together always. Okay? At some place, recombination is happened. At the other place, generation should be happened to keep the total number of free electrons and free holes in semiconductors. Otherwise, imagine that recombination is happened, 100 times every single second, but generation is happened, 10 times every single second. Then maybe a few minutes later or a few hours later, even a few days later, we're gonna have tremendous number of free electrons because many, uh, no, not tremendous number, very less minimal number of free electrons left behind because recombination rate is much faster than the generation rate. then we're gonna lose all the free electrons in the end. Does it make sense? You just place your silicon sample on your desk. A few days later, you're gonna lose all the free electrons. Even though the silicon sample is well doped with arsenide, as we have learned, the arsenide, the total number of arsenide is identical to the total number of free electrons. That's what we have learned. But if recombination rate is much, much faster than the generation rate, then you're going to lose all the free electrons in the end. It doesn't make sense. And it may not be happening in nature. So recombination is always associated with the generation. And its rate is similar to the rate of generation. Okay, that's a very introductory remark for chapter 3. And from now on, let's dive into more details on drift first. Okay, okay, let's break here because I would like to quite often give you some break time. Then you're gonna focus on my materials and my voices with more efficiency. Okay, so I'm going to stop here and please have a short break time by yourself, and then please take a next movie clip. Okay, see you in the next one.